skin of dreams. My skin. My skin of dreams. What heart denies? What mind defies? What lay beneath? This skin of dreams. My skin. My skin of dreams.
How's it going, guys? Volume level good? Everyone can hear me? Guess we're gonna get started in just a couple minutes here. Waiting for our friends here. Cool. Looks like we got somebody over on Twitch and somebody over on YouTube. I think everything looks all right on my end here. Right now, I'm just running some tool simulation on a part that I made, I don't know, probably 2 years ago. This was an HDPE drone frame they had cut out for a little small 3-inch racer. So I wanted to make sure that Mastercam was working with the live stream today, so I was just testing this out. You know, last week when I tried to fire up my Mastercam, the video didn't want to display at the same time as we were live streaming, so we were stuck with just a blue screen. But we figured that out. Something with the video card, it doesn't like to didn't want a hardware render at the same time that the stream was going on, so I had to disable the hardware rendering on the video card and drop back down to just the software rendering, which is a little slow and not ideal, but you know what, we can see, and that's what's important. I guess in a couple minutes I'm gonna fire up some pre-recorded video that I've got during the week. Since last video, I took the 4-inch frame that we were designing and cut out a prototype on the laser real quick, just out of black acrylic plastic, something easy to laser out, but it's a good proof of kind of a proof of concept, a little visual aid. We can see what it's going to look like when it's done without wasting expensive carbon fiber. It would also let us test the fit on our motors, flight controllers, our hole clearances, stuff like that. Make sure that we haven't overlooked anything or missed something. So we'd be able to check the fit of our parts on it. So I've got that made, and I've shot video over at the shop, setting up the laser and running that part. And then we finished designing the camera mount last week, and so fired up the 3D printer, and I got some footage of that I'll show everyone. Fired up the 3D printer, loaded up with some Ninja Flex Semi-Flex, so the medium stiffness Ninja Flex, black TPU material, and printed a camera mount out of that. And I'll show you how that went. I'm not crazy about printing the flexible material. I have a Robo 3D, and it's not the extruder. It does great in all the other materials. I've even been able to print polycarbonate, but the distance from the drive rollers to the extruder head, it's a little big, and so it likes to jam up on the TPU. I modified the head a little bit with some Teflon tubes, and that certainly helps, but there's some drawbacks. One of them being I don't retract the material anymore when I'm printing TPU, because doing the retracts led to a lot of jamming. So just getting rid of the retracts helped to make more successful prints. So hey guys, who's in here so far? We got a couple more people in there. I don't know why the heads up or our lower thirds doesn't show how many people in YouTube there are. The Twitch number looks good. The Twitch number's right. Looks like there's 3 people over on YouTube, 2 people over on Twitch. I don't know. I don't have a display of who's in here, so let's see. Hi all. I gotta fish you guys out and get you guys talking, see who's in here. So, anyways, this was just a little tool simulation that I threw up. As I was saying, this is a 3-inch quad with a 1306 motor in it. made out of HDPE, about half inch HDPE. This is Op1. So this is the first operation. And it's done on a router. So I would cut a sheet about that size. And this would be the first operation. It's a 1/4 inch end mill. I believe it has, yeah, it's got a corner radius on it. And we clear out all these pockets. We got 2 tools on here. 3 tools. 3 tools on there. So I come in, drill the holes, switch to the to that 1/4 inch. No. 3/16. Well, anyways, so I run around with the end mill, do all the pockets, then come in with a chamfer mill, put all the little chamfers on all the edges here, and then the last thing I do is I switch to this 1/16, 1/8 inch cutter, just the 1/8 inch end mill, just to cut the part out. That's the final operation in the set. But the part's not done. After this, I flip it. It goes onto a jig. The part gets flipped upside down, and all these pockets get chased all the way through. What's up? Hot glue. Benny Mac says had to hot glue the tube on my extruder mod so it wouldn't move during retraction. Yeah. Yep, that's kind of like the same thing I have, like that little Teflon tube that sits between the drive wheels and the extruder head. In the retract, it just keeps banging up against the drive wheel, and eventually it wears down to the point where the TPU can get past it and form a little loop in there, and then the thing's jammed up and you gotta take it back apart. So the nice thing on the Robo 3D is that the head comes apart super easy. You know, you could just release the back of the head and you can pull the filament out and you can get to the drive wheel and clean it up super easy. So it's not toolless, but it's just 2 Phillips screwdrivers and you basically have the whole thing apart. So you're running the TPU successfully on the on that $63 3D printer deal that you posted about. If that's the case, I'm going to be really sorry that I don't have one. I would have one just as a backup or just as a second one. For $63, if it works, that's great. There's my frame. There's the finished frame. I like this quad. It was a fun quad to fly. Super easy to race. I outgrew it a little bit. It wasn't quite fast enough at a 3-inch. So the new blue one that I have, that's a 4-inch quad, and that's like my sub 250 racer, and it's the same. It's kind of the same design, except I separated the 4 arms, so they're 4 individual parts. The main reason for doing that is just for nesting. Instead of taking up this much room on the sheet, when you cut it, when you machine the arms out separate, you're like way down here. It uses like less than half the material. So, anyways, I can get rid of that. Pop over to SolidWorks. There's the pod that we were working on with Smarky. Benny Mac had to replace the extruder arm that broke and modify the replacement a bit. So a couple catches to doing the $63. I suppose as long as you're a capable person, that printer's probably going to be fine. I guess if you've never touched one before, it might be a little bit too much if you need to start modifying it to get it to work, because you might not know, you probably won't know what exactly you need to do in order to get it working, because you won't know what's really the root of the cause, right? Problem. I don't know. I thought those prints that Frank posted looked pretty tight. Probably about the same as most of the printers, up to $800,000 are probably You probably can't tell them apart. I can't believe that though. $63. I don't even know how you ship that for $63. I kind of know, but still, it's crazy. Save my Smarky Pod. You know, the other day we were putting the GoPro, getting the GoPro mounted up on the WBX frame. Right there. That's the GoPro version of the pod. You can see the session sitting up on there. And our little strappy holes for the battery strap to run around the session. It's not a fully caged session. It's a little exposed. It's a little naked. But it's a good deal. The pod gives quite a bit. That helps protect it a little bit. So Benny Mac says that that $63 printer worked well out of the box and with TPU. It's just the stock extruder armor always breaks, and the aluminum replacement has a bigger gap to span. Yeah, the replacement has a little bigger gap. I see. So out of the box, that stock arm's fine with TPU, which that's nice. But I guess if it breaks and you're stuck with the aluminum anyways, well, that's not too bad. I don't know, it wasn't too bad. I think the hardest part about modifying mine was finding a Teflon tube that was just the right size. You know, it had to have the right inside diameter in order to fit the TPU through, and it had to have the right outside diameter because my extruder, the injected molded plastic part, you know, it had like an 1/8 inch hole in there, so I had to find, you know, just the right tube. The first one I got, it didn't fit, and it didn't fit by just like a couple thousandths, and it would not shove down into that hole. So anyways, I eventually found a little tube and got that running. I still don't like printing the TPU. I mean, once it prints nice, but I don't know. I don't like having to babysit the printer because I'm always nervous that it's going to jam up on me. I'm wondering if Bob's here. I know I wanted to make sure Bob saw some of the stuff we were up to. A couple of them, they've been really interested in the casting that we did last week. Oh, yeah. Can I even bring that up? Where is that? I've got we dropped down in durometer on this pod here. So the first two pods that we cast were out of that 65D urethane, which turned out to be a little bit too stiff. So if you smashed it with a hammer, you could, you know, we got it to break. Which that's the fun part about prototyping, is the destructive testing. So anyways, Smarky got to beat on that thing with a hammer, and we were able to get the 65D hardness urethane to break. So we dropped down to 45D, and the 45D urethane is pretty squishy, like dog chew toy squishy. So we're probably gonna settle for something maybe in between the two. But it wasn't bad. Real quick, here's you have mounted. Ben says you mounted a session on it yet? No, because we didn't make a silicone mold yet for the session pod. So we made the silicone mold for the standard pod, and we're starting to pull parts out of that mold. And the next step is Smarky has to print out the GoPro pod, and once that's printed out and cleaned up, sanded down and primed and ready to go, then we're gonna pour the second mold. It'll be a 2-up mold, so that we can get 2 pods with each casting. And then we'll start making both the regular and the GoPro pod. So haven't had the session up on that. There we go. So anyways, a quick recap of last week. This was making the silicone mold for the first pod. There's the standard raggy pod sitting in there. That's just an ABS plastic printed part. And then it's primed and sanded, and then painted with like a black texture. And there's our boy Smarky stirring. Here we go. So this is the first part of a 2-part silicone mold. You can see pouring the silicone right into the corner, and then you let the silicone just flow over the top of the part. That way you don't trap any air bubbles in there. There she goes. And that guy's got to sit there for 24 hours. The silicone takes forever to set up. But man, I mean, it's durable stuff once it's set up. I mean, this silicone you can even cast metal into it. It's good stuff. There we go. So that's the first part of the silicone mold. Popping the part out of there. So that's our ABS 3D printed part, and it's backfilled with what's that clay called? Plasticine clay. That way the silicone isn't going to flow inside of the pod, so it's completely gated off. And there she is, all cleaned up. All the plasticine clay has been cleaned out of that part, and time for part 2. So there we go. We've got to put the part right back into the mold, and not the fanciest job cleaning up the support material on that one, but she's good enough. There we got all the toothpicks and a little pour spout made out of plasticine ready to go. So all the toothpicks, that's what's going to let the air out of the mold when you start pouring urethane into it. And mixing up the second batch of silicone. And there she goes, filled up. Another 24 hours, and then we got to demold that. There's our 2 halves. All right, so there's the internal cavity for that pod, and when we put those 2 molds back together, all you're left with is the gap between it. There she is. There's our mixing cups, and yeah, so we mixed up a set of 65D, which is like the shore hardness for the urethane. So we mix that up, cast that in there, and it takes like 10 minutes for that to set. You can feel it. It's 2 parts, 2-part urethane, 1-to-1. So you mix up, what was it? It was like about 20 grams of each one. Throw those together. As soon as you start mixing them in a cup, you can feel the cup getting hot in your hand, because when those 2 chemicals meet, they give off heat. Their reaction. That's actually what cures the plastic. And there she is. There's the part number 1 out of the mold. So that went pretty good. A couple air bubbles in it, and we've modified the mold since then in order to let those air bubbles find their way out, so we're not trapping them anymore. But there she is. You can kind of see some of the texture that's on there. When you do this, when you cast these silicone molds, absolutely every little detail that you leave on that master part gets picked up by the silicone. So if you can still see 3D printing lines on your master part, you're going to see 3D printing lines on every part after that. And there's part number 2. We put some purple pigment into the urethane when we cast it. Of course, we're starting with like an opaque white urethane. So the purple is pretty light, but I think it fits right into the rest of Smarky's color choices. There she is. All right, so that was last week. And if I hop over to this week, sorry about that. Let's turn that off. Turn off my jams. There we go. Okay. There's our new part. So that's the 45D. Lot squishier. It's a cool translucent white. Awesome if you put LEDs behind it. It's gonna look really cool. But man, it was super, super soft. Can I loop that? Oh, yeah. This milky white stuff would look awesome backlit with some LEDs. But I think we got to step up to something that's halfway in between these two pods. So the 65 felt like regular plastic. It was just like ABS. You know, I guess it maybe had it has a little bit of give when you squeeze real hard, but basically it felt like plastic. And like I said, Marky smashed it with a hammer, it was able to crack it. So we figured we needed something a little bit softer that's going to give in a crash. So we dropped down to 45. 45 to me looks like it's going to be so soft that in a crash you're going to end up like damaging your camera because it doesn't have enough strength to stop that impact. So the next part that we cast is probably going to be like a mid 50s for durometer, something right in between the two. I think we'll be happy and start banging these things out. So Smarky was saying that it hardened up, so it fully cured overnight, and it's a little stiffer than this. This is fresh out of the mold. You can see it's like a dog chew toy, super soft. Very cool though. That's enough of me poking at that little thing. All right. Let's pop over to what we were doing. Let me bring up the quad. Refresh our memory here. Save Smarky's work here. And we'll open up our 4-inch stream quad here. Stream quad. Number 1. There she is. Cool. Our heart and crown frame. So anyways, we're going to start. We want to look at cutting this guy out, and we're looking at our 4mm carbon fiber there. Okay, so I think a little bit later today we're gonna open this up over a Mastercam and program the router to get that cut out. Before we go blasting that thing out of carbon fiber, I just wanted to make sure that she looked okay on the laser first. So real cheap, real easy to throw it on the laser. So here I am, we're over at the shop, and I'm setting up the laser. I'm importing the DXF. Okay, so back to SolidWorks here. Okay, so what we did last week was we took the top view of our frame and we saved it as a DXF file, which is just a 2-dimensional drawing. So let me just call this number 2, and I'll walk right through this. So here we go. We're going to save the current view. We're exporting the current view, and okay. And there. So that is the 2-dimensional outlines of the frame, right? Super easy, nothing complicated about that. That's exactly what I want for both the router setup and for the laser setup. Don't need a 3D model for either of those because they're both 2-dimensional parts. There's no pockets with varying depths or anything like that. It's all, everything is a through hole. Super easy. So cancel out of that. And pop back over to our video. Okay, so there we go. We gotta bring in the bring in that DXF into the laser software here. It comes in a whole bunch of tiny line segments. So right there, real quick, I was just uniting all those tiny little line segments into one continuous line. Here I'm setting up the origin position, so where the laser is going to start. I picked the lower left-hand corner. Right, and the grid there represents the table on the laser. Just positioning where I want the part. And then I'm coming up to the laser settings here. Okay, so these are basically the only settings you have on the CO2 laser. You got your speed, you got your power. So the speed, I'm not even sure what that is. It might be, oh, I don't even know. I couldn't tell you if that's like millimeters a second, maybe. Probably millimeters a second. The power is a percentage. So power of 100 is 100% of the laser's power. 25 is 25% of the laser's power. And then corner power, when the laser comes into a tight corner, you need to back off on the power, otherwise it'll melt a bigger hole out in the corners. So that's like about a 80 to 90% of your cutting power is your corner power. And then overlap is not something that I ever need to use. And not blow while laser, and always blow. That's the wonderful Chinese translation for the air assist in the nozzle.
How many watts is the laser?
Benny Mac is asking how many watts is the laser. I've got a 150 watt tube in my laser. It's got the 3 foot by 4 foot
full power laser
table on it.
Fun.
So I'm setting up. I threw a black sheet of 1/8 inch acrylic in here. I thought that I had some scrap laying around that was big enough, so that back with settings here. So I'm using a speed of 15. I'm using a power of 50, so half the laser's power, and the corner power I'm backing off a little bit, just setting that to 40. Okay, I settled in. And so the next step is just to save that file and then upload it to the control on the laser. Give her a name, Stream 1, and then head over here to download. And those are all the files that are sitting in the machine controller. I just add this to it. There it is. That over to the controller. Okay. So then I just have to scroll down and find Stream 1, that file, and throw my sheet of acrylic in my laser. See, I've got like a slat bed sitting in the laser right now. It's a little dirty and she cleaned up. There it is. So, little scrap sheet of 1/8 inch black acrylic. Acrylic is like the easiest cutting part in the world. It's perfect material for laser cutting. Edges come out really nice. Everything's like got a real nice flame polish on it. Here I'm jogging the machine over, so it's got a little red. The red dot there is just a basic laser pointer. There's nothing fancy there. That's not what does the cutting. That's just so that I can see where the laser is going to hit the material. So here, what I'm doing is I'm focusing the laser beam. So the beam coming out of the tube is about 1/4 of an inch round, and that is too big to cut anything, right? It'll burn 1/4 inch lines and stuff, but it's way too big to actually cut through any kind of material. But the reason the beam is big is it's the only way to have the laser bounce off a mirror without it actually carving a hole into the mirror. So the beam starts off big, and that way the power of the laser is spread out across the mirror. So the beam starts off as 1/4 of an inch, and of course the properties of a laser, right? That the beam is pretty much straight. It doesn't spread as it goes. Like a regular light bulb, the light spreads out the farther it goes. So the laser does that, but not much. It's basically a parallel beam all the way to the head. So it comes out of the laser tube and hits, let's see, it hits 1, 2, 3, like 4 mirrors on its way over to the head. And inside the cone right here, there's a tube and a needle valve which adds air into the nozzle, and the air does 2 things. It protects the lens. The positive pressure inside of that cone means that none of the smoke can get up into the nozzle and land on the lens.
Matt Fenderia Physics
And then
3.
the other thing is to blow the material out of the way as it's cutting. And so you've got that 1/4 inch beam all the way to here, and inside that cone there's a lens. That's the final part, the final optic, right? Is that lens, and that lens focuses just like it's a magnifying glass, just like burning things with a magnifying glass in the sun. So that takes that 1/4 inch beam and focuses it down to a really tiny spot. And the spot size on this laser is about 8 thousandths of an inch. That's the kerf in the material that it leaves behind. So the piece of material I'm holding right here is the focal length of that lens. So I have it marked with a Sharpie, and all I have to do is bring the lens down. Right? I have to back off on the collet there and bring the lens down a little bit until it's flush with that line. And then I know that the focal point of that lens is dead nuts on the top of the material. So that's where the focal point of your laser is where it's going to do the best cutting. So now she's in focus. That looks good. And back over to the control, and I'm going to set the origin. So that's its reference point for where to start from. I hit the test button real quick. So when you hit the test button, setting the origin, then hitting the test button, test. And it draws a real quick square. So as long as you're not wandering off your material, now I know where the part's going to end up. So shut the door, hit start. There she goes. So the cutting beam is infrared, so it's invisible to us. We can't see it. If you have a camera that's sensitive to infrared, you can actually see the beam. Like if you've ever, took a cell phone camera and looked at the remote for your TV and you can see that purple light. If you did something like that, you could see that beam, but it's invisible, which makes it ridiculously dangerous to have that machine open and have that laser fire, because you can't see the beam, and if it hit you in the eye, that'd be the end of your eyeball. Oh, there she is, working its way around. Laser's super nice. You don't have to clamp the material down. No, nothing's gonna move. Nothing. There's no contact. All you have to do is keep the mirrors clean and keep the lens clean, and everything's good. The CO2 tubes, you only get so many hours out of them before they need to be replaced or refilled with more CO2. It leaks out over time, but I don't have a ton of hours on this machine because I'm not cutting parts over every day. But it's just so nice to be able to throw a sheet in there and
Pavlok
go
716,
button.
would it cut off a finger?
Would it cut off a finger? Pavlok wants to know if his laser would cut off a finger. It would. If you... I don't know. It might. I think the laser would probably have to go pretty slow. You'd have to set it pretty slow in order to get through like a half an inch or 5/8 or whatever thickness your finger is. But I guess if you handcuffed somebody in there and wanted to try to snip the tip off, yeah. I've seen some people that will tattoo themselves with the laser. You know, it kind of looks like burning a hot dog, you know, with a hot utensil. Before it turns black, it kind of has that white. It is.
Ben Bino, Mr. Bond. I expect you to lose a digit.
Oh, Benny Mac.
Block 716 water jet at school was pretty dangerous.
All right, cool. So. You go away. I have cats on me. All right, bye-bye, cats. Okay, let's see. Yep. There we go. So, there's our little acrylic part. Hold that up to the light there. Came out nice. It's a good-looking frame. Right? Not too bad. I still think the arms are skinny. It scares me. But I like it. I like this design. It's cool. Very happy with it. Water jet at school was dangerous? Yeah, the water jet will go through anything. Yeah. The laser won't go through everything. It only goes through certain materials. It has to do with the type of the light, because it's infrared. If you try to cut a material that infrared can go through, it won't cut. It has to be a material that infrared light cannot get through. That's how it ends up cutting it. It gets hot, blows its way through there. But yeah, the water jet's no joke. The water jet will go through anything. That's on the list of things that would be really awesome to have. Water jet. I've been following the couple of people that build the DIY water jets out of a pressure washer, like an off-the-shelf pressure washer. You know, you end up getting you get a hydraulic booster to raise the pressure, and then you get a mixing nozzle to run the sandblasting sand through, or whatever the media happens to be. And it's kind of the same thing. Like you just throw your part on the bed, and you don't really have to hold it down that well. It's not like running, aluminum on a mill where you have to make sure the part's not going anywhere, and fixturing is just such a huge part of metalworking. But man, with the laser, the water jet, throw the sheet up there and blast through it. That's awesome. So yeah, there's our first prototype frame. It's not gonna last. You could fly it. I've flown acrylic before, but even if you came down and landed rough, that'd be the end of these arms. They would snap right off of there. Polycarbonate would do all right. A polycarb frame would be good, but I don't know. The acrylic's just so easy to cut. It was a good way to visualize the frame. Now I get to actually hold the frame and see what it looks like. That's cool. So I don't know. Let's pop over. The other thing that we did this week while we were gone was we threw the Havelock 716 camera mount in the 3D printer. Ran that out of some NinjaFlex CPU. So here's the machine. This is the Robo 3D that I've got. And there it is, just kind of touching off. And there she goes, starting to lay down the first layer. My bed looks dirty, but what that is ABS slurry that I've got laid down on top of my bed. And so I don't really scrape it off. I just kind of add to it if I need to. But let's see. Oh, you guys can't see that because I'm being silly. There you go. Now you can see. So, anyways, back to the beginning of the video. Touching off. This machine's got auto bed leveling. so it touches off on 9 points of the bed before it starts printing, and there's no leveling the bed. It just goes. It does all the calculations for what it needs to be height in order to make the good part. I'd say this thing came out pretty good, and I didn't have any problems. CPU came out perfect on the first one. Very strange. Good luck today. There we go. What did I use? I set this up with Cura, the latest Cura build, and it's got like a two-layer wall, and the cubic infill, the cubic subdivision infill. That's my favorite infill, and that's available in Cura. I like that infill because it varies the density based on how thick the part is. So in the thickest parts, the infill will drop way down and be super light, and where the part is thin, narrow, it raises the infill density. So it makes a really good strong part and keeps the weight down by being variable, rather than having to pick 10% infill and then having that 10% infill across the whole entire part, and you've got mushy areas that need to be stronger. Cubic infill, awesome. Cubic subdivision, I should say. Oh, there she is. It was a 14-minute print, so 14 minutes for a little camera mount. Not too bad. It could be faster. I think I'm running it around 60 millimeters a second is my speed. I'm speeding the video up in a couple spots here just to keep it going. Ooh, painfully slow on the 3D printer. Not like the laser to blast it out. The laser program was a minute and 20 seconds to cut the frame out. That was with 50% power. If you wanted to go faster, you could just turn the laser up all the way to 100% and you could go faster. But it's a light bulb basically, so the higher wattage, the higher you run your laser, the shorter the life you end up getting. So you're running at 50% and taking a minute to cut one frame out.
That's another thing about the mini printer. Only 30 mm/f.
There you can see it laying down the outer walls. Yeah, you can kind of make out some of the infill. There it is doing the infill. And there she is. Fast forward to the end. So I was saying earlier, I don't have the retract going for the TPU, because when I retract the TPU, because it's such a flexible filament, a lot of times it'll jam. And that's just terrifying when you're like 2 hours into a build and then the filament decides it wants to jam. So I've turned the retracts off. So it's like a hot glue gun when you pull the trigger and the stuff just keeps flowing out even though you're done. That's what it's doing. So it's making all this like stringy mess as it goes back and forth between these two towers. But it's so easy to clean up those strings that it's not worth the aggravation of trying to dial in the retract. I just take the side cutters and snip the material off with the side cutters, and then I take my torch, the little butane torch, and you just kind of real quickly go right over the top of the print with the butane torch, and it melts off all the little stringies. Melts them right off, and it looks beautiful when it's done. So there's that print. Now if I let me bring up the old microscope. Ooh, it's big in there. This way. There she is, 716. 716 in memory of Havelock's second place win this winter. Pretty slick. Yeah, let me see if I can get this up on the other camera. It might be easier. So there she is. Focusing. Focus. It'd be cool. That guy's gonna fit on here, right there. Camera mount there. Ooh, I didn't do that yet. And that looks awesome. I love it. Looks very cool. With a little 716 representing up on the front of that. I like it. This is cool. Coming together. And I might want to even screw that together. I don't know. We don't need to screw that together just yet. I want to make sure I get to some of the programming for the carbon fiber part here. So that's that. Not too bad so far. Right. Let me fire up Mastercam and pick up where we left off. So we've got, there we go. We've got our frame. And I think, let's say it's time to set up the router for our carbon fiber. And so we gotta come up with a little bit of a strategy over here in Mastercam for that. All right. Where do we start? Start by loading up my machine settings. I've got a Shop Saver. That's my router. So I'm going to load up my Shop Saver. And get rid of that. There we go. So here's my Shop Saver. I'm going to start by setting up my material. So we were looking at Dragon Plate last week online and kind of getting prices for sheets of carbon fiber. And I think like a smart thing to look at was like a 2 foot by 2 foot sheet of 4mm carbon fiber. So I'm going to put that in. I'm going to put in 24 inches by 24 inches, thickness of 4mm. And my origin, my starting point, is going to be on the bottom of that carbon fiber plate in the lower left corner. I want to display it on the screen. Yes. Okay. So here's, I don't know if you can see that very well after it comes across the internet, but there's a wireframe of that sheet of carbon fiber. So that'll give me an idea of where I am on the machine. Next is going to be importing our file. So I'm going to go find that DXF, that two-dimensional drawing that we exported out of SolidWorks. Over in the stream, DXF. There we go. Okay, so our quad is gigantic and it's way bigger than a 2 foot sheet of carbon fiber. So what's happening here is that the DXF it's not a smart enough file to tell Mastercam what units that we were working in. So it thinks that every millimeter is an inch. So the part's gigantic. But all it takes is a little bit of math. You got to convert those inches back down into millimeters. And I have that saved. We're going to multiply it by 0.03937. That's going to convert our inches back down to millimeters. There she is. That is the proper size. So our red box is our 2 foot by 2 foot sheet of carbon fiber. And here in the corner, we see our little 4-inch framey. So I'm selecting that and I need to move it up onto the sheet. So Mastercam's not quite as nice and friendly, at least not back in Mastercam X4. Not as friendly as SolidWorks. It's a little old school. But that's all right. It gets the job done. So I need to move this thing. I'm going to move to origin. That's the operation I'm going to do. So I've selected my lines. I'm selecting move to origin. And I'm going to click where do I want origin. We know that our 0, 0 is the corner of our sheet, that red box there. So I want that corner of the sheet to be over here. That's where I'm going to click. Okay, so it moves my part up. and puts the origin where I clicked. So that'll be enough room to come around and cut that part out without our tool leaving the material and coming back in. We don't want to do that. So there we go. Okay. I'm going to hold this part down with either vacuum or with spray adhesive. Both of those work really well. I kind of like spray adhesive better when there's lots of tiny parts that the vacuum can't hold on to very well. I would say that this one's a really good candidate for the spray adhesive, just because of how like thin these arms are and stuff. That the vacuum's not going to hold on to that part very well when it comes around. When we do the spray adhesive, I'll show that as well. But what you have is you'll have like a film, a protective film that comes on the carbon fiber sheet in order to protect it from scratches. And what that's good for is I'll spray that sheet of carbon fiber with Super 77, 3M Super 77, right? And then slap it down onto my spoil board. And when it's time to pull the parts off, the film stays behind, stuck to the spoil board, and I just pull the parts off of there, and they're perfectly clean. That film that it ships with keeps all the spray adhesive off the carbon fiber sheet, and it holds on really well. It holds on too well because it's actually when I do the spray adhesive, it's pretty hard to get the parts back off the spoil board of the machine. So anyways, a strategy. We're gonna work from small to big. So we're gonna do our smallest features on this part first. We don't want to cut the part out first. Cutting the part out is going to be the very last operation, because once we do that, then this part is going to be somewhat free to move around, right? If we cut it out first, then we wouldn't, we would have a hell of a time trying to drill the holes after we cut the part out, because the part's going to want to wander around. It might not be much, but because it's not attached to the main sheet anymore, it has the capability to move when the cutters are entering those holes. So cutting the part out, very last operation. First thing we're going to do is we're going to attack these small holes. So let's head up to our operations here. First thing I'm going to do is pull up a drill operation, and that's going to be for our 2mm holes. I think we've got a bunch of 2mm holes, and then we've got 4 3mm holes for our flight controller. First thing I'm going to do is I'm going to start with the smallest ones. I'm going to start with these small holes, right? In Mastercam, that's a mask on arc operation. That's going to allow me to select one hole, and then I can select the whole entire part, and it's going to find all the matching ones. Or not. One more time. Drill, mask on arc. This one. Select my arcs. Okay, there she goes. She found them. Okay, so it went around the part and found all the matching hole sizes. And I'm going to say, yep, that looks good. Okay, we're doing a drilling operation. I need to pick a tool. These are our M2s. I have two carbon fiber cutters right now. One's a 16th, one's an 8th. So let's just plunge in with that 16th. That 16th end mill. So I'm going to look for a 1/16 end mill. End mills. 1/16, 8th, 16th. There we go. Okay. This is just a generic end mill, and I need to kind of change it over to my carbon fiber end mill real quick. So I'm going to edit the tool, come over to the parameters, And I say it's made out of carbon, or it's made out of carbide, not high-speed steel. And we're gonna run that at 48 inches a minute, and we're gonna plunge at 20 inches a minute. And my spindle on my machine can go 23,000 RPMs. And these end mills don't really have flutes. So I'll get one out for you over the microscope, and I'll show you what these guys look like. So yeah, so there's a carbon fiber cutter. Doesn't really have flutes. It has all these diamond cuts on there, right? It's more of a burr. They kind of say that you can use 5 flutes as a rule of thumb in the data sheet for this cutter, but I'll show you the way I do it. I just fire this up as a 1 flute cutter, and that way I can see the chip load on 1 revolution. So if that makes sense to some of you machine operators out there, I'm gonna tell Mastercam that the tool only has 1 flute, and it's gonna tell me, it's gonna feed back to me how far the tool is moving every revolution. Okay, so my feed rate of 48 means that every time the tool turns, it's going to advance 0.02 of an inch. That is an acceptable load on that tool. You usually have to go back and pull up a data sheet that the manufacturer provides, or like talk to the sales rep and figure out how hard you can run these tools. But I've run the 16th end mill before. I did it the wrong one. Of course I did. Back in there, 48, 20, 20, 1 flute. Okay. All right, so yeah. So we're advancing 2,000s every time that tool goes around, and that burr is capable of getting rid of the chips that are coming out, or the kind of the dust and the carbon fiber. Carbon fiber doesn't really make much of a chip, but at least those burrs are able to get rid of that material going that fast. If you go too fast, like let's say you take this up to like 4,000s every revolution, right? Now we're traveling at 92 inches a minute. Those burrs don't have a deep enough gullet to evacuate the cut material, and they end up clogging, and then you start burning and making a mess and breaking cutters. But this little 1/16 end mill has no problem running at 46 inches a minute. The spindle's running extremely fast. The spindle's going 23,000 RPM. But we're not cutting yet. We're drilling. I'm just gonna back that off to 20 for this drilling operation. Okay, so set up the tool. Now we're gonna go. Let's see. Standard operation, standard drill. We're gonna set up our heights, right? So our retract height. How high do we want to start from? We got a 4 millimeter thick sheet of carbon fiber. So let's start at 6 millimeters, right? If you remember, we set our origin. We set our origin 0 to the bottom of the carbon fiber plate. So if we're 6 millimeters up, it means we're only 2 millimeters above the carbon fiber. So I'm going to put in 6 millimeters there. Our top of the stock, that number's already been established when we set the stock up. And our depth, we are going to go not to 0, we're going to go a little bit past 0, so that we clear the back side of that plate, and we're going to dive down into our spoil board a little bit, and that's why the spoil board is there, right? It's just a sheet of MDF, and it's sacrificial. So we're gonna go like not that deep, like 15 thousandths past the bottom of the sheet. Negative 15 thousandths past the sheet. That's better. Okay. Yeah, once you go past 0, you gotta start putting in negative numbers. Okay. Our home point for the machine is 0, 0, 0. That's different for everybody, but that's for me. There we go. Okay. That's the operation. These lines are where the tool is going to travel. And if we want to preview it, we can take a look at the simulation, right? So there's our drill bit. In this case, we're just plunging with an end mill. There's our tool holder. And we can preview it. So it's going to come around. Whoop. Oh, here, sorry. Let me put that where you can see it. Goes around. The next arm, plunge, 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 plunge. Next arm, plunge, plunge. Done. All right. So Mastercam can tell me how long that's going to take. And so when you're figuring out how much this stuff is going to cost you, he's going to, you're going to add up all your machine time. You have a shop rate, just like your auto mechanic probably has a shop rate. Like your mechanic might charge $100 an hour at his shop. Well, the CNC machines are going to be the same thing. The machines are going to have a rate, so many dollars a minute. I usually go off of real simple $1 a minute to run the machines, and that covers your machine cost and wear and tear and the cost of electricity. And so the machine needs to be, if it's running, it's making, $60 an hour, just to cover, that covers the expenses of the machine running, right? So you're going to factor that stuff in when you make these parts. Like, okay, I just spent, I can look it up. So we spent a total of 16 seconds drilling the holes. If I know we're making, if this machine's $1 a minute, then I can figure that, we're chewing up about 20 cents going around and drilling those holes.
Havlock 716, does it just rapid from hole to hole in between the holes?
Yeah, it's just going to rapid. Havlock's asking if it rapids from hole to hole. Yeah. My machine doesn't do like 2,000 inch a minute rapids. It's slow. It's like a 220 I have it set to. 220 inches a minute is the rapids on my machine. So it's not super fast. It's still got stepper motors. They're big stepper motors, but they're still stepper motors. And if I cross over 300, start missing steps, and that sucks. So I limit the machine to about like 220 inches a minute. Okay, so there you go. There's our first operation. We drilled those holes. These are also small. So I'm going to use the same tool, and I'm just going to add those points. Same thing, mask on arc. Oh, I know what I did wrong. Go. Those. Enter. There. So added those 4 points, and it added it to the end of the operation there. Okay. We don't need to watch that again. If you really want to know what it looks like, you can do the full simulation, right? So there we go. There's our sheet of carbon fiber, and you can see it went around and drilled a bunch of really tiny holes. Very fun. Okay, next operation. Now, I think we've got a... Oh, we can switch tools. Okay, so now we're going to do a tool change. We're done with that little 1/16 end mill. And now I'm going to pull up a my 1/8 inch end mill. and we're going to finish drilling the larger holes, and we're going to drill the 3 points of the crown. So another drill operation, mask on arc, select these arcs, found 4, perfect. We'll start there and we'll add the 3 for the crown afterwards. We're going to select a different tool this time. We're not going to use that 16th. We're going to go up to our 1/8 inch end mill. 1/8 inch end mill. There we go. That's a generic tool, so I'm just going to edit that real quick. Carbide. And we could probably run about 60 inches a minute with that. And again, I'm gonna tell Mastercam that it's got 1 tooth. Mastercam doesn't make any adjustments because of that, but when I come back here to this feed per tooth window, it's gonna base that calculation off of 1 tooth. So it's gonna tell me, telling me that that tool is advancing almost 3 thousandths every revolution. We could probably take that up higher, 3 thou. Yeah, that'll be fine. So we'll run that at 70
FPV, sorry, anyone
70
listening?
inches a minute there.
Havlock
We're still
716,
drilling.
why doesn't the mask on arcs pick up the radius in
I'm
battery
getting ahead of myself.
slots?
We're still drilling, so I'm
Does
backing
it
down
work for
like
complete
half.
circles or any arch?
And our parameters, same thing as the other drill bit, and we're gonna go through, let's go through 20 thousandths past the bottom of the sheet. There we go. Add 4 more points. I want that point, that point, that point, 3 more points, sorry. And regenerate my toolpath. And perfect. I can play that if I want to. Come through. So we've added 5 seconds onto our time. There she goes. This is that's not full speed. Just playing back a little bit slower. Okay. That's good. I think the next thing we got to do is drill these 2 slots out. So real simple. I'm going to come in. I'm just going to draw a quick line down the center to attach my tool onto. So a line and a line. Perfect. And instead of a drilling operation, now we're going to do a contour operation. Okay. It's going to tell me, okay, select a contour chain. And that chain is going to be that line and that line. Those are the 2 lines I want to cut. Okay, my tool, 1/8 inch end mill.
_FPV,
and now we're cutting. So I'm going to bring that thing up to 70 inches a minute so that we're feeding it 3 thousandths per revolution. We're going to plunge into the material a little bit slower though, because it's not a drill bit. Smarky's here. What's up, Smarky? Why does the mask on arcs pick up the radius in the battery slots? Why doesn't it? Yeah. Either I might have drawn the slots. Havlock is asking why that mask on arc didn't pick up the slots. I believe it does look
Mark
for
Prayer.
a full circle, and that's why it didn't grab the crown
like.
either. It's looking for a complete circle as a drilling operation. That's what it wants to see. And yeah, it's the same thing with the slots. I'm pretty sure that it wants to see a complete circle because it's a drilling operation. So here, over at 1/8 inch end mill. Where'd it go? Yeah, did I say 70? Faster. Okay, so 70 inches a minute, and over to our cut parameters. So this is, we're gonna set up our setting up our cut here, and I chose to attach the end mill to that center line. What I have to do is I have to tell Mastercam that it is not supposed to do any kind of compensation. I don't want the tool on the left of that line. I don't want the tool on the right of that line. I want the tool to go dead center down that line. So compensation type, I need to turn it off. You can see this little icon here. This little blue arrow is in the center of the tool. If I turn compensation on, you can see that the little icon of the tool is off to the side.
My voice sounds hot.
So we're going to go back. Turn the compensation off. It's going to ride the tool right down the center of that line. Super easy. Depth cuts.
716 cutter comp.
We shouldn't need to do a depth cut. Actually, I might do the depth a different way. No, I'm gonna plunge in and just blast it out. So lead in, lead out, that kind of stuff will come later. We can't have any lead in, because of this slot. We're just gonna be plunging right in, and then coming across full depth. Okay, linking parameters. So here's our heights. Here's our height setup. Our retract, quarter inch is perfect. That's high enough. So our rapids are going to be up at a 1/4 inch. Our feed plane is going to be 0.1. That's that might be higher than our retract. Let's put our retract up at a 1/2 inch. Okay. There we go. Top of our stock, there it is. Our depth, we want to blow through the bottom, so I'm going to go like 20 thousandths past the bottom. And my machine home is at 0. Okay. So let's take a look at that path. Perfect. If I look at it from the side, you can kind of see that that turquoise line does come past the bottom of the sheet. It's probably hard to tell on the live stream, but it does. So anyway, I can preview it and make sure it's good. Yep, plunges in, moves across. It's rough on the tool, but like I said last week, these tools are basically throwaways. So you can be rough on them, load them up. As long as it doesn't pull the fibers up, as long as you keep a sharp tool, it won't affect the surface quality too bad. Okay, slots are cut, and next thing we got to do is cut out our internal holes. And once those holes are cut out, then we can blast the outside of this thing out and free our part. So we're gonna set up another contour, and we're gonna select our heart. And it is going to be our same 1/8 inch end mill, and our cut parameters, we have to turn that compensation back on, right? Because we want the tool to be on one side of this line. So turning the compensation back on. Depth cuts, we should be able to, we can blast the 4 millimeters out. Kind of I guess a rule of thumb would be is if you want a good surface finish with these little carbon fiber end mills, only go as deep as the diameter of the tool, and then you can run fast and have a good surface finish. I'm going to be going a little bit deeper than the diameter, but the tool is still rigid enough to deal with that. So no depth cuts. We're just going to go. I'm not going to lead in, lead out. Lead in means that instead of plunging right up against the line, the tool would plunge out here, out away from the final contour, and then it would ramp up to it, and that'll give you a cleaner outline. If when I just plunge in, you'll see a tiny little dimple in the final part from where I plunged, but I'm not concerned about a tiny little dimple that I don't think anybody would notice, except for everyone watching the stream now, because I just told everybody. But we're concerned about going fast and efficient. All right, so there's our cut, and we're on the correct side of the line, which usually doesn't happen. Usually it's always on the wrong side. We can preview what that's going to look like. I want to check whether we're climbing or not. So I'm going to preview that. See which way the tool's going. And we climbing? Yes, we're climbing. Okay. So climbing has to do with the spindle going clockwise on my machine and what direction we start that contour in. Most of the time you're climbing, and if you picture a rotating bit, if you picture a clockwise rotating bit and your material is towards yourself, you head to the right, you're climbing. So as that tooth comes around, if you can picture it, that tooth is trying to climb up on the material. If you're a woodworker, most of the routing that you do is conventional, because conventional routing, conventional helps hold the material up against your fences when you're woodworking. Whereas if you were to try to run a piece of wood through your router in the opposite direction, which would be climb milling, the router's going to want to like throw the piece of wood at your chest. Crown. Let's see. Another tool path. Contour. Pick our contour. That one. And you're going to see where it's going to stop short here. 1/8 inch end mill. Cut parameters. Good. Making parameters. I want to come out the bottom of the sheet. Done. Okay. That 1/8 inch end mill can't get into that tiny gap there. So if I preview what this looks like, we can see what's going on. Okay. All right. Our cutter is too big to cut that crown out. Can't get through there. So what I'm going to do is, when we have the smaller tool loaded up in the machine, that's going to be when I cut the contour out for the crown. All right. So I'm going to delete that operation and come back into my tool paths. Redo this one. Suppose I didn't need to delete it. All I just needed to do was change the tool. But anyhow, so our tool, we're going to go over to our 1/16 inch end mill. And we're going to feed it at 48. That's going to be about 2 thousandths per revolution. And this time, I'm not going to plunge that tool all the way through the 4 millimeters and try to run it around. What we're going to do is we're going to take some depth cuts. So I'm going to set up the initial parameters here, which is we're going to come out the bottom. I'm going to retract a 1/2 inch above our spoil board. And we've got 2 choices to do here in Mastercam. We can do depth cuts. Okay, so if I turn depth cuts on, I can say, well, if this material is
working on my
4 millimeters thick, let's say we take a 2 millimeter pass and then another 2 millimeter pass, and then we'll be through our material, right? That's one option. The other option, and the one that I like, is instead of doing just a 2D contour, we can do a ramp. Okay, and what that's going to do is that's going to slowly feed the cutter down into the material as it goes around. So it's not going to plunge and cut, plunge and cut. This way it's constantly feeding, very slowly feeding the cutter down. And I'm going to tell it that every time it works its way around, that it should get 2 millimeters deeper. And we could round that up a little bit to like 0.085. Okay, and then once it's all the way to the bottom, I'll make one more pass at full depth. Okay, very good. So there you can see that it's going to go around 3 times, right? It's going to start at the top surface of the material, and it's going to slowly ramp down in the material. And on the second pass, it's about halfway through the material. and then on the third pass, it's all the way down to the bottom. Nice and easy on the cutter. You can see that it just barely squeaks, right? It doesn't get all the way through there. We could cheat. We might, we could go back to SolidWorks and open that up a little bit. But I think we might be able to leave it. Let's see what it looks like if we simulate that material. There you can see it making its cuts. Boy, it just leaves the tiniest little sharp little piece there. Let's catch up with Smarky. Smarky, how's the hotbox going? Should we tell everybody about what kind of hotbox we're talking about? Instead of just jumping in chat and saying you've got a hotbox. Building a hotbox. So, going back to that, to the pod that we were casting, right? Smarky, I think you missed it. You weren't in here yet. So,
Smarky _
back to our squishy pod.
Matt Fender Wind Tunnel. Block 716. I bet it's pink.
The this urethane, this 45D urethane, it hardened up overnight. And got stiffer than when I shot this video as soon as we pulled it out of the mold, and it hardened up overnight. And so what we're thinking is we should post cure in order to speed up the process, because waiting 12 hours overnight is terrible. So to speed up the process, what we're going to do is post cure these parts. That means is after we pull it out of the mold, or even when it's in the mold actually, we're going to put it in an insulated box and bring the temperature up over 100 degrees. That way the materials are curing faster. What I was saying earlier, it's a two-part, this urethane's two parts, A and B. When you mix them together, the chemical reaction starts generating heat. And that's how the plastic cures. The heat from that reaction is what sets it.
Smarky
so if you can bring the temperature up on the materials, it sets faster. It's in the mold. You have a part? Smarky's got his first part unassisted. Smarky, tell me you got an unassisted part in the hot box. That's awesome. So Smarky was over here at my place doing all the these first couple prototypes, and I've been teaching him how to cast this urethane stuff.
UV resistance on that PU?
The UV resistance, if we put pigment in it, it would have more. I don't know what the UV resistance is. And because the part doesn't actually sit outside,
Smarky
I don't think it matters.
FPV, no, the old one.
The old one's in the box? Oh, okay. I was going to say, I was excited. I thought maybe Smarky cast his first part. You have to shoot video when you do. We all want to see what this is going to look like. You in the hot box, silicone, the pink silicone molds and everything. Your family's got to think that you're crazy. I mean, my family thinks I'm crazy when you come over here and we're playing with all these chemicals on the kitchen table. So anyway, so we're thinking that we need to like raise the temperature of this thing so we can get the part to its final hardness faster. And so Smarky had called up the folks at Smooth On, and he said they were super helpful, and they said, what you should do is look at building a hot box, because if we can get the part up to 150 degrees, it's going to cure a lot faster. And so what I believe Smarky did, and correct me if I'm wrong, is just get a sheet of that polyisocyanate foam, amber colored foam with the aluminum foil on the two sides, from Home Depot or wherever, and just built a little box out of it and put an incandescent light bulb on the inside of it, and that's just going to raise the temperature, just a little bit, hotter. This stuff should be cast at 75 degrees, but not too many people keep their house at 75 degrees. So we're just gonna hopefully raise the temperature inside the box to, 90 degrees, 100 degrees, and we should be able to cycle these parts faster that way. So that's cool. I'm excited to see your little hot box. All right, back to here. What do we want? We had a little sharp piece there. Sharp pieces. Yeah. We gotta get rid of that. So let's do a little cheating. Let's go into that. We're gonna edit this and stock to leave on walls. I'm gonna cheat it and say rather than leaving some stock on the walls, why don't we like dip into the walls a little bit? Like let's say 5,000. Let's see what that does. There we go. Perfect. So what I just did was I told the program to go 5,000ths of an inch past that contour. So that crown's going to be a little bit bigger than what we drew it, but it's just enough so that the tool can get through there and we won't be left with any sharp little points inside there. All right, is that, what do we have left? Oh, we got these left out on our arms. So last contour, we need circle, 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 circle. And we're back to our 1/8 inch end mill, running that at about 70. And we could ramp it. We could ramp that down in there. I don't know if there's much of a point. No, let's not ramp it. Let's just dive in and cut it. About 20,000ths out of the bottom of the sheet. There we go. And I'm 2 for 2. I got 2 on the wrong side and 2 on the right side. That's usually how it goes. Okay, so if you can see, my tool path is on the wrong side of the of our contour there. That one's right, wrong, right. So I have to fix that. So I'm gonna pop into the geometry tab and find those. What did I say? This one? That one wrong? Let's see. Change. Hello. Change side. There we go. Reverse. No, which way do I want to go? Okay, there we go. If you take a look, oh, I zoom in, but the arrows don't get any bigger. Anyways, there's a long arrow and a short arrow, right? The long arrow is what direction the spindle's going to be traveling in, and the short arrow is which side of the line the cutter's going to be on. So I just have to take a look at these and fix them. Change side. Oh, you're all changing side on me. Change direction is what I want. Chain, sort, rechain. Reverse. Okay. There we go. Reverse. Okay. I got them all go the right way. Regenerate. Did I do it right? All on the inside? All on the inside. Okay. Last operation. Our final contour. This is it. We're gonna cut this guy out. Let's see. So if we were climb milling our internal holes, we were going counterclockwise in order to climb mill. So our outside contour should be clockwise, right? Counterclockwise on the internal holes and clockwise on the outside. So there's our arrow. We're headed around clockwise. That should be good. Okay, our tool, we're running our 1/8 inch end mill at 70. And we'll go the whole depth. And we'll come out the bottom 20 by 20 thousandths. Okay. And we're on the correct side. And if we preview this, beautiful. There we are. One pretty little 4-inch frame cut out. All right. I've got one more thing I want to do before I call this done. If I cut this part all the way out like this, there's a good chance that when the tool comes around at the very end, before it's finished, this whole part is going to have a tendency
_FPV suite
to move, because there's nothing holding the part in anymore except for the adhesive, spray adhesive that's just on here. Before, we had the strength of all that spray adhesive. Now all we have is the little bit of spray adhesive left on there. So what I'm going to do is just add a couple tabs in there to make sure our part doesn't go anywhere. That way we don't get any chatter or worse right at the very end of this cut. So I'm going to edit my parameters, and I'm going to go to this tab. All right. And I want to put tabs in here, and I want to manually place them. I want to be able to pick where the tabs go. Okay. And this tab motion is the size of my tab. Okay. So when the cutter is coming around, it's going to pick up a little bit. The cutter is going to lift up for just a short distance and then plunge back down in. That's going to leave behind a little tab that's going to hold our part. So the ramp angle is the angle it's going to lift up at. The width of our tab, let's say 0.3 inches, I think is just enough to hold it. The carbon fiber is super rigid, so it doesn't have to be a huge tab. And we're going out the bottom of the sheet 20 thousandths, so we need to add that to our tab thickness. So let's say 40 thou. So at the end of the day, we should have like a 20 thou tab. And I need to place my tabs. Okay, so I'm going to put a tab on each arm. Like so. And then pressing enter when I'm done. Yes. And I'm regenerating my tool path with that new feature there. So now when we come around, if you look at the tool path, you'll see that we got a little bump in the road there. It's going to pick the tool up for 0.3 inches, right? And then plunge back down. That'll leave behind some tabs for us. If we preview it, you can see exactly what we're doing here. There she is, right? We got 4 little tabs in the corners. That's going to hold our part. It's going to keep it rigid and make sure that at the very end of this cut, when this part is free, that we're not getting a bunch of chatter at the very end because this thing's sliding around on the table. Worse is if this part lets go, your cutter will grab it and snap your end mill off and ruin the part. That's no fun either. So let's take a look at the whole entire operation here. Make sure you guys can see that. Pull that up. Back the speed down a little bit. There she goes. Okay, first operation, we've got our little 16th inch end mill going around doing our clearance holes for the 2mm. And then we're grabbing that 1/8 inch, doing those slots in the heart. We're going to go, I'm going to change the order of operation so that we're not changing tools twice. But here we are with our 16th end mill. doing the contour of the crown. Because we got a thinner, more delicate tool, we're not doing it in one pass. We're going to take some depth cuts to make sure that that tool is not bending. So a couple times around, 3 times around, and that's out. That's a little bit dangerous right there because I didn't do that operation as a pocket, so I've got a little chunk laying in there. If that chunk moves the wrong way, it's gonna break my tool. But I'm willing to risk it for the sake of speed. I don't want to spend all the time machining that little
Smarky
dangler out.
PV, nothing worse than a bent tool.
Yeah, don't want to get stuck with a bent tool. Yeah, we got a couple of little pieces that are gonna come flying off the machine at us, but that's what safety goggles are for. Or as our friend says, they're safety squints. I like that. Engage the safety squints. Cool. So that's it. That's programming the machine. The last step, let me see. Find that 16th tool and make sure that it is, there it is. So that's my 16th tool. I'm going to rearrange the order of these and get it back up top. So 16th, 16th, and then the rest are 8th. Okay. So very last step is to output the code for the machine. So all these CNC machines, even the multi-million-dollar machines, they're running off a G code. Your 3D printer is also running off a G code, and so we're going to generate that G code. I'm going to select the whole entire group, and I'm going to come up to this little button, and I'm going to post operations. And here we go. There's the program. So all of this, how many lines do we have? So 510 lines. Oh. Yes. Yep. Line 510. Yep. 510 lines. So here he is. If you can understand G code, you know exactly what this is. When you're 3D printing, all your 3D printing software handles all this. Like in the background,
Mastercam's programs
in the background, Cura is handling the G code for your 3D printer, and the G code tells the extruder head what to do. If you can, I don't know if you can read this on the live stream, or if it's just too small. I don't think I have any way of blowing it up any bigger, but all it is XYZ position, right? XYZ. So it says go here, go here, go here, go here, go here, go here, go here. Each line tells it where to go. That's really all there is to it. If you can, once you can start programming machines, you start to kind of recognize some of the codes that are in here, especially if you have to fix your programs manually because your post stinks. But I can see that these G81, right? So that's a drilling operation. So G81 means drill, and then the XYZ location of that's where the hole goes. Drill another hole here, drill another hole here. Each line is where to drill a hole. And then we come down here. These G1s, that's just a standard feed. So if you see, it says G1 Z 1.57. So the spindle's going to go down to 1.57, and this F20, that's the speed. Feed 20. So 20 inches a minute, the head is going to go from 257 down to 157, and then so on and so on. And go here, 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 go here.
Is a drilling can cycle.
That's it. Yep, yeah, the G81 basically kind of the drilling can cycle. I guess for anybody else that wants to know like the can cycle, it just kind of like a shortcut. So all you have to do to drill a hole is type G81 and then tell it where to drill the hole and how deep, and the machine will figure out the rest. So you don't have to, it doesn't take like 4 lines of code to move the head over and then plunge into your material. It's just 1 line of code, and the machine knows what to do from there. That's like your can cycles are. So all those G81s, that's all our holes. Yeah, that's it. There's our program. 500 lines of G code. And at some point in time, people actually knew how to like type all that stuff, which is crazy. I can't even, yuck, right? But I don't know. Get used to looking at it. I know which lines turn the spindle on and off, and which ones are circles and which ones are straight lines and arcs and everything. Fun stuff. So, anyways, program the machine. I think for the next show, I'm gonna head over. I'm gonna get a sheet of carbon fiber and go over to the shop, and I think we try to cut one of these out of carbon fiber and see where we're at. I think we still have maybe some cleanup to do on the main assembly, right? We
had to type it in high school before they
we need a top plate for this guy, and we need a way to hold our video transmitter and antenna and receiver and stuff.
Matt Fender, it was always short programs.
That's what next week will be.
Lines.
Next week we finish up our top plate. Our top plate will give us somewhere to mount these 2 guys. I don't know, looking good. What do you guys think? Short programs. Fender says you had to type G code in high school. Man, does high school still have programs like that? So something tells me they don't do that anymore. I wish I did that in high school. That would have been great. We didn't have anything like that. No. We had just a little, I think we were basically catching the tail end of like shop class. I had like one woodworking class.
Matt Fender project lead the way.
We did some like graphic art stuff on some old Macintoshes. That's probably about it. Project lead the way.
Havlock 716. Yeah, my teacher made us write out 500 lines.
Havlock says my teacher made us write out 500 lines
can cycles.
In a roughing cycle.
Havlock 716 right.
Next day we learned can cycles. That's nice. That's what a wonderful way to teach you, huh? Right? Man, I've never had to like really handwrite anything. I usually have to fix the program. I've modified my post a couple times to get it better, but it still has some problems with it. Shop Saver doesn't exactly have like platinum support with Mastercam, so you're on your own for getting a good post in order to generate the G code. So I've worked on the post a little bit to try to fix little goofy errors here and there, but there's still a couple left. Like I don't know if you were paying attention, Havelock, but all the drilling cycles were all at the very top of the G code, right? They're at the top of the post. Should have been down after the
electronics,
after the machine like homed itself, and after the
project was the core sequence.
At least after the spindle turned on, right? If I fired that up, the thing would start drilling holes with the spindle turned off. So I don't know. I haven't been able to figure out why the post keeps putting all the drill cycles at the very top, but I have to like copy paste those into the proper location. It's one of the few things I have left in the post that I haven't been able to figure out. But the post, yeah, you have to know G code in order to like fix the CNC programming, and if you need to fix the post, that's all written in C. So you got to figure out how to program in C in order to fix the post.
The machine.
Yeah. She's not bad. I don't know. It's what I learned. my buddy showed me Mastercam, so that's that's like the direction I headed off in. So I took it from there. He got me started in Mastercam. Mastercam is what we were using in the wood shop that I was working in when we were designing arcade games. All that stuff was done in Mastercam. So I taught myself Mastercam so that I could give the guys in the wood shop a break and not design parts that were just ridiculously hard to actually machine out. So that's one of the things. It's like your teacher forcing you to handwrite out the G code. You can appreciate things that way if you've seen what it takes to do it. You can appreciate how hard certain things are. So like by teaching myself Mastercam and how to like program the machine and run the machine, all of a sudden I stopped sending like ridiculously hard parts down to the wood shop to be cut out because now now you understand that if I draw this part like this, the guy programming the machine is going to want to come up here and like chop my head off, because once you've done it, you understand what you're asking somebody else to do for you. Anyways, it's just about 11 o'clock. Just about 2 hours in. Cool. I don't know, guys. Anything else? Did I miss anything for today? Pretty good. I don't know. Smarky. I fire up the laser video. Nope, not there. There we go. Laser. I just let that roll for a little bit. So yeah, anyways, that's where we're at. Hope next week we'll have a carbon fiber frame cut out. And this weekend, right?
Block 716, good
So
time.
this weekend we've got some racing down here in Boston. Just yesterday I ran the idea by my buddy who has a shop on Boston State, and he was open to the idea of letting us race up in the showroom because he's not using it. He's using all the mechanics bays and stuff like that, but he's just using the showroom for storage for the time being. So I asked him if we could throw a racetrack in there on the weekends, and he said, "Yep, go for it." So I don't know. We got a few weeks to wait before all this snow melts and the fields dry up. So I figured we're gonna do a 8-week season. Right, so we'll do March and April. That'll give us 8 weeks. Just do points. We won't do we'll still have like a championship race or whatever, and we'll have a good time, have a little party up there. But I guess the payout at the end, I'm gonna base off of your season points, and everyone will be able to like drop 2 out of the 8 races, for their point total. So like if you can't make it. It should be too big of a deal. It won't affect you that much until you miss like 3, and then you would be points, right? So you can miss 2 days without losing any points. Like I said, Saturday and Sunday, so whichever day is better. I know some people haven't been able to come out on Sunday, so those people can come on Saturday. You can come on both days, whatever. It'd be the regular time on Sunday, so get there like around noon and start setting up, and then like be racing by 2 o'clock. Saturday night would be I'm gonna go down there at 4 o'clock on Saturdays and start setting up, and so you can wander in at any time, and we'll just hang out there until we're too tired and get kicked out for being obnoxious. But I don't know, I'm gonna start dragging all my cool stuff down there, so we'll run the projector, run the sound system and everything, get it bumping in there, fog machine, I don't know, whatever. We got a lot of toys that we got to get out. That'll bridge the gap until we get to our summer flying with our 5-inch and 6-inch and unlimited and all the good stuff, 6-cell, 8-cell, whatever you guys got going on. Plus our 250-gram class. That's the one I'm looking forward to. I'm looking forward to the 250-gram stuff. And I gotta talk to RNL, but you'll still have Fridays up at RNL. I don't know what time. What time do you guys go to RNL at Fridays? I never went up there on Fridays, so I don't even know what time normal for RNL on Friday. Figure the same thing. So you guys up in the North Towns can still hit up RNL on Friday. You don't have to drive that far to get out to Boston.
Hot Block 716 I will try.
It'll
May only
save
make
me
a
some
few.
driving too, because
Going to give the wife a few weekends
far.
before outdoor starts.
6 o'clock. Okay.
Smarky underscore F.
I posted. I started posting events in the Facebook group, so
Ben B 6
I'll go check the time.
Friday
6 p.m.
RNL.
All right, cool. I'll go adjust the time. I don't know what I wrote down for RNL. Did I write down 7 maybe? I wasn't sure, so I just threw a number in there. But anyways, I'll fix that. 6 o'clock on Friday at RNL. All right, cool guys. I think that's it for me. Marky, Ben, Havelock, Bender, whoever else hiding in there. Anonymous numbers. I'll catch you guys. I'll catch you guys later, and see everybody on the stream next week. All right, cool. See, I think I have credits. Credits. Yes? I don't know. Oh, there you go. Cool. All right. So Saturday in Boston is like a practice. Yeah. So this Saturday especially is going to be like just setting up the track and seeing what it's like in the building and arranging stuff and figuring out like, I don't know, where power is, what we need to do. There's power in the floor. Like there's all those little like brass receptacles all over the floor in there. So we just gotta figure out like, I don't know, where we're gonna set everything up. Where do we want like the pits and stuff like that? If you got folding tables, bring folding tables. I'll bring a couple folding tables down there. You know, it's not like RNL where we got all the really nice pits and stuff set up. So we're gonna be on our own with that. But I don't know, we'll deal with it. Same thing as like flying outside in the summer. You know, bring a table, set up your stuff, and I don't know, it was pretty roomy in there. The ceilings aren't as high, but there's still plenty of space. And I'm starting to build the baby bando parts, so it's gonna give me a place to like put the baby bando parts, and we can race on that stuff. Cause I got a bunch of video that I need to shoot for the baby bando, and so yep, when all that stuff's down there, I'll be shooting video for more bando commercials and what have you. So, cool. I guess I'll see some of you Saturday. All right, I'm out. I'll catch you guys later.